In the previous lesson, we looked at the type of differential equation that is first order, and that first order differential equations can be re-expressed into something that is separable. We call that the homogeneous differential equation. In this lesson, we're going to still look at first order differential equations, but this kind of first order differential equations come with a special property. This kind of differential equations will go in a, what we call it, a linear differential equations. And it looks very particular, they're very special. It would usually consist of y prime. It would also consist of y itself, and then that will be it. There would sometimes be a term in front of the y, and there will be another term on the other side. So you are looking at an equation that looks like this: y prime plus something of y equals something else. Or sometimes you may see y prime, something of y, and then something else. It looks like a quadratic equation, except that this is dy dx. When we are solving a first order linear differential equations, we need to come up with an expressions that will give us these two terms on the left hand side when you differentiate it. Now, looking at the property on this left hand side, you are adding two pieces together, and there is only one thing in derivatives that will give us a plus in the middle, and that is the product rule. So we are going to come up with something that will give us this plus that after you apply product rule. But as you can see, usually when we apply product rule, it comes with a function at the front and then finish it with another function. And as you differentiate it, you end with f prime of g, f prime times g plus f times g prime. We see the prime here, and we see the function itself there, but this is missing from the equation here. And we are going to multiply the entire equation by the extra term that we are missing at this time. We will use something called the integrating factor to decide what is missing in your equation. And as you multiply this entire equation by that extra term, you will be able to turn the left hand side back into a product of two functions at the end. So once again, we're going to find the integrating factor that will make this left hand side differentiable. This integrating factor, once you've multiplied this integrating factor to the entire equation, the left hand side will now be the result of your product rule. The result of your product rule, giving us the left hand side. So this integrating factor can be obtained by using this equation here, by integrating this middle term and have base e raised to the power of that. That's how you get your integrating factor. So what we are going to do is to look at example number 1 to see how this integrating factor can be obtained, and then solve this differential equation. So here, in front of your y, we have 2x. And that means this integrating factor can now be obtained by using base e to the power of this dx. And we can integrate this. This turns into e to the power of x squared. And that means we will now multiply this term to the front of this, to that, and to that. So here we have e to the power of x squared times by dy dx plus e to the power of x squared 2x times y, and on the right hand side e to the power of x squared times by x. And you can start to see how this 2x in the equation would then be the chain rule as you differentiate that part here. So on the left hand side, I can conclude that this left hand side would be the result of the product rule including this and that. So as you differentiate this function, for the first part, part 1, differentiating this and leave it alone give us part 1. And for part 2, when you differentiate this and leave it alone, here comes the chain rule from the first one. On the right hand side, as we continue, let me this time put the x in front of it, make it a little bit easier to look at. And now as I integrate both sides with respect to x, the integration and the differentiation on the left hand side will simply turn everything into e to the x squared times y. And on the right hand side, as I integrate, I'll be using a u substitution here. Let u be x squared, and we will have du equals 2x times dx. And that means with the x and dx here, I need to get rid of the 2 from the right hand side. And on the right hand side, that means the whole thing would actually turn into one half e to the x squared plus c. And finally, as I divide this to the other side as well, we will end up with 1 over e to the x squared of this, which can be simplified to 1/2 plus c over e to the x squared.